software vendors or different machine vendors, they provide the reliability, which is 5-9 reliability. They never claim that the reliability is 100%. The reason is usually we feel that as if we go for a better vendor or more reputed vendor like Google, Apple, or Cisco. So possibly we can have the 100% reliability, but actually it is not so. The problem is not with the machine. In fact, the problem is with the fact that impossibility of consensus. So first we'll try to understand what is consensus, then impossibility, then how is the life beyond this impossibility. In general, the consensus and agreement, these two terms are used as synonyms, though they have little difference, but here it is not very important to highlight that difference. But the problems are usually called the agreement problems. In fact, these two are related. So the blue list that shows the different problems which are related to agreement, maybe leader election, mutual exclusion, or many others. So the important thing is that when there is a decision about any of the activity or any computation, like we have the last example, air traffic control system. So all the pilots, they have the same view of a particular flying area, so that to avoid the collision, they can have the correct decisions. So to provide the correct view to everyone, or single consistent view to everyone, is a challenge. So all these problems are consensus problems, and if there is no failure, if we consider a very simplified scenario, so if there is no failure, then of course consensus is very trivial. Easily it can be achieved. Simply we broadcast to everyone, and every recipient will have the same information, and of course the decision will also be same. But once there is a failure, then of course that makes the life difficult. Failure could be of any kind: software failure, hardware failure, or communication failure. So that makes the life difficult, makes the consensus difficult. This is another example. For example, say we have multiple sensors. For example, if you are sitting in a room or in your home, and if you want to know the temperature of your home, so this is, for example, you have placed say 4 sensors maybe in the 4 corners of a particular room. So these 4 sensors, they provide some input value, and naturally you know that because sensors are at different places. So some sensor is in the corner, some sensor might be somewhere else. So each sensor will have a different reading. So they propose, but because you want to know the temperature of your room, so this value V, that has to be same for everyone. Means all the sensors, eventually they need to agree on this value V. And this value, the most important thing is that this value cannot be an average value taken from all the sensors. This value has to be some input from a particular sensor. This is an example of consensus problem, that sensors reaching the consensus designers. Like in the same manner, we know that temperature of like sometimes we hear in the media that minimum temperature of a particular city, like say minimum temperature of Chandigarh or maximum temperature of Chandigarh. Though we find that it's very interesting to know that even the 4 sensors in a particular room, they are providing the different reading, and we are claiming that this is the minimum temperature of Chandigarh. This is actually the process of consensus. Maybe another example I can quote just to make you comfortable about what the consensus is. For example, say like we are conducting an online course, online talk. So in an online interview, for example, there are certain experts, and say those experts, they cannot join simultaneously. Like to join this talk, all of us have to sit simultaneously, not at one place, but simultaneously. So if experts do not sit simultaneously, for example, they're busy or they could be any other region, then separately each expert can interview the candidate, and he can decide that candidate has to be hired or not to be hired. And later on, after this interview, and this similar process has to be repeated for every candidate. And later on, all the experts need to communicate with each other or transfer their input, so that finally they have to reach to a particular consensus that a particular candidate has to be hired or not. So this is another informal example of understanding the consensus. Very famous theorem about the consensus is just I'll read the text. In a purely asynchronous distributed system, the consensus problem is impossible to solve if even a single process failure. So that's a very famous problem. This is by Fisher, Lynch, and Patterson, also called it the FLP problem. So that is a very famous impossibility result that says that in a asynchronous, purely asynchronous, means it is impossible to solve even with a single failure. So if we talk about, if this theorem is true, then there is no question of fault tolerance. If even in an asynchronous environment, if even single crash cannot be handled, then the question is how to do it and what is the life beyond this theorem. So another implication of this theorem is an impossibility triangle, that because in a distributed computing environment, if fault tolerance is something very essential. Okay. So out of three, fault tolerance, agreement, and termination, we can have any two at a time. We cannot have all three. And this agreement represents the safety property in liveness. Later on, we will discuss what is safety and liveness. But out of this, only two. So if we consider, because we are going to talk about the fault tolerance, so if we consider that fault tolerance is indispensable, then of course we have to dispense with either agreement or the termination. So that is another important result. That is an implication of FLP impossibility. Similarly, there is another very famous theorem about shared data systems. It's called the CAP theorem. C stands for consistency, A for availability, and P for partition tolerance. So consistency means every client, every user has a consistent view of a particular data or shared data. Availability means everyone has an access to a machine, and the fault partition tolerance is if some machines have gone faulty, even then the application is running or it continue to be executed. So also out of these three, only two. Eric Brewer, the famous computer scientist, so he gave this theorem that out of these three, only two you can have only two. Means either you can have CA or AP or CP, and of course this zone is prohibited zone. We cannot have all three. An example we can consider that in a relational database system that satisfy ACID properties. Example is MySQL. So there is strong consistency because we have already seen. So it has strongly consistent. But the NoSQL systems which are used in the Google or other huge databases or in the cloud, so they satisfy eventual consistency. Means every time all replicas or all servers, they are not they don't have the right consistency, but eventually after some time they will have the consistency. So this is another important result. So within these two, means FLP impossibility and CAP theorem, we will try to capture that where there exists a room for consensus. So for we try to understand the system, what kind of systems we have in hand. In an asynchronous environment or in an asynchronous system, there is no bound on any either on the processor speed or on the message communication basically the delay in communication. So there is no control over the system. Means in fact a totally asynchronous system or purely asynchronous is a kind of chaos. It is not actually a system. It does not follow any bounds. But within that, because the life is asynchronous, within that we try to put some bound on the system. Like in a network, we send some message, and we expect that after some time this message will be delivered. For example, this can be done by the experience. Like say you post a book to your friend, and if that book is not delivered within 3 days, so you may assume that the book might be delayed. But if book is not delivered, say even after 1 month, then you will assume that possibly the book is lost in the transit or lost in the post. So that's how we decide. We have some bound, and that bound can be decided with the experience with the system, working with the system. So this is called the partial synchrony assumption. Means we have some assumption about the timing of communication delay or mid processor speed. So that's how we divide asynchronous, and we can say in one line that a synchronous system is just a special case of asynchronous system. Some example I can say, like say if for consensus, if there is a input vector, for example, say 5 machines or five processors give input 1 1 1, then of course the decision must be 1. Similarly, if all are giving input 0, then of course the decision must be 0. So that's a consensus, because the consensus value cannot be a value which is different from all the inputs. It has to be value at least from one of the inputs. However, if the input is like this, some are 1 or some are 0, so then in that case, decision could be 0 or 1. So that is one simple binary consensus example. Another example I put, which we see that, for example, say there is a 5-set tennis match, and at a particular stage during the match, the score is like this 6-3, 6-4, and in favor of A. Then we can say it is a bivalent state. Means from here onwards, match could go in favor of A or in B. That's why we say it bivalent, 1 or 0. However, if the score at some point of time is 6-3, 6-4, and 6-1, then we call it a univalent state, because here onwards decision can only be in favor of A, and that's why beyond this we do not continue the match. The moment the score is like 6-3, 6-4, 6-1, we declare that match is in favor of A, because beyond this. So this is another example of consensus. To see it from the execution point of view, machine point of view, for example, we start with this just a small dot, if you can see on your screen, that if is the initial state, if we conduct an execution, say alpha. So after execution, say some configuration C is achieved. So we say that in this area of the triangle, shaded triangle, we find that out of C, if we consider that this white triangle is the area where decision can be only 1, and black triangle is the area where decision only can be 0. However, there are some shaded area where decision could be 0 or 1. So that's why C is called a bivalent configuration, where we can reach 0 or 1. However, after another execution, say beta, we reach a state or configuration D. There onwards, it is not possible to modify the decision. This is a univalent or one-valent. D is one-valent configuration. Similarly, E is a zero-valent configuration. From there onwards, the decision could be only 0. And 0 and 1, if you think of especially in the terms of transaction processing, it could be commit or abort. So the question is, what kind of failures we are faced? Because actually we are trying to build a fault-tolerant system. Rather, we are trying to achieve consensus in a fault-tolerant system. Then what kind of failure we are faced with? So failure, they are categorized into 2, and this is all because one is called the fail stop and the Byzantine. So Byzantine is basically the arbitrary failure, where any kind of failure that can happen. Here also we do not have any assumption about the failure, and out of that, if we have some control over the failure, then it is a fail stop. So fail stop is it is also called the fail silent failure. Means machines, once it fails, afterwards it doesn't do any activity, it doesn't provide any input, it doesn't execute any command. So that is called the fail stop. Fail silent also means once it has failed, it will be silent. But however, in the Byzantine, a machine can be sometimes it is working correctly, sometimes it is not working correctly, sometimes giving the correct result, sometimes incorrect result, sometimes arbitrary result. So we say it is a Byzantine failure. So fail stop is that's why it's a very simplified form. It is called very simplified failure, or also in terminology of distributed computing, it is called a benign failure. And however, the Byzantine is called the malign failure, because we're a very nice kind of failure. Like being a faculty, say if we are in a class, so we find some of the students who are not interested in my lecture, or who are tired enough. So sometimes in the last bench they are sleeping. So sleeping means I like them because they don't disturb me. Once they're sleeping, they are not disturbing. However, some students, sometimes they create some nuisance, and sometimes they are very sincere also. But that is the Byzantine behavior. So just try to understand this in the environment. So these kind of the failures we are faced with. So if you consider the simplified scenario of a crash failure, this is also called the crash failure. Crash means once machine has failed, then afterwards it doesn't do anything. So it is very simple. Flood set is a very common algorithm. You might have heard about it, but just to have a quick recap of this, that here every process has some input, and each one will broadcast in input to all others. So eventually everyone will have the same set of inputs, and after that it can decide. For example, say you have a scenario where there are 100 banks. 100 banks are connected to a particular network, and if you want to know which bank has the minimum balance, then using this flood set algorithm, the balance of each bank will share its balance to other banks, and eventually all the banks will have the balance of every individual bank. So from that set, it can find the minimum balance. So that's why every bank will be able to know that which bank has got the minimum balance. Similarly, you are trying to find a minimum number or maximum number, anything. So it's a flood set algorithm. So that is for crash. Means if a machine has failed, then of course it doesn't do anything. Here, if we have an algorithm, the question is how we declare that algorithm is correct or incorrect. So for that, there are two famous properties. One is the safety, another one is the liveness. So safety means nothing bad ever happens. Means machine does not perform any wrong action. That is called the safety. And liveness means eventually means now or sometimes in future, it should perform the correct. So it means nothing bad should happen, but at the same time, you cannot do nothing at all the time. Sometimes you need to do something good. So that's why for any algorithm, if it is not doing something wrong, that's fine, but eventually it should do something good also. So that is called the safety and liveness. So if you have an algorithm, propose an algorithm, we need to prove that whether safety and liveness properties are satisfied. These properties, safety and liveness, mapped with the consensus problem. So in the consensus problem, safety and liveness is translated into three problems, that is termination, agreement, and validity. So this is all about the safety and liveness together. Like a termination means eventually every process must decide. If you are like we have seen that the tennis match example or sensor example, means eventually every match should be decided that in favor of someone. So that's how termination means they should terminate. And once it is decided, it cannot be changed. Like once you declare that player A has won the match, then you cannot change this decision. So that's how termination. Second one is the agreement. Means all must agree that this is the decision. Means if you say that match is favor of A, then everyone should say it is in the favor of A. And third one is the validity. That if input is same, like say out of 5 sensors, every sensor is telling or providing information that temperature is 25 degree, 25 degree, 25, 25, 25. That eventually you should declare 25 as the room temperature. It cannot be any other value. So everyone starts with the same input, then finally the decision must also be the same. So that's how termination, agreement, and validity. And here we see that all these properties, it can be represented in a different form also, like in a crash failure. That was a generic example, but in a crash, so termination, it is decided that it has to execute for f+1 rounds. The question is why f+1 rounds, where f is the number of faulty machines or faulty processes. So soon we will see why it should be f+1. And second is that since processor introduces no spurious messages in a crash failure, because once system has failed, then it will not take any action. It will not execute any command. It means afterwards, there will not be any input from that machine. So that is no spurious messages. And third one is that at the end of f+1 rounds, so many rounds of execution, that each one will have, like I've given the example, that set of balances of individual banks, and that must be the same at every bank or every site. So that is the agreement. So in this way, these things happen. Now here, for correctness of the algorithm, there are two requirements. Number one is the number of processes, number of machines that should be more than f+1. Minimum it should be f+1, where f is the number of faulty machines. So this is lower bound here. It should be minimum f+1. That is one, and that's why it's a statement that there should be at least f+1 rounds. The question is why f+1 rounds? We can see from these slides. Like for example, there are f failures, and why f+1 round? We assume that in one round, one machine fails. F failures means total f failures. So for example, in round one, say process PI sends value of X and it fails. Now in the round two, PJ, which has received the value of X, it sends value X to PK and it fails. So similarly, the failures are on. And at the end of F round, PF has sent the value X to PN and it has failed. Now you see that in all F rounds, in every round, there is one failure. So total failures are F. If there are F rounds, at the end of F rounds, about X, only PN knows. For example, if X is the value of, say it is the minimum balance of bank B1, this value. So the minimum balance of bank B1, it is only with PN. No one else is aware that what is the minimum balance of bank B1. Now it might so happen that PN may declare that B1 has got the minimum balance because nobody else is aware of X. However, other processes, they do not have the balance of B1, so they may declare some other bank having the minimum balance. So that's why if the decision is taken after F rounds, this decision could be wrong. And in that case, agreement will be violated because PN will declare that minimum balance is with the bank B1. By other process, say PI or someone may declare that minimum balance is with bank B2. So there will not be agreement, there will not be consensus. But however, if we have, say, F plus 1 rounds, just we increase one example, F plus 1 rounds, then what will happen? So in F plus 1 rounds, there are total F failures. And out of this F failures, in the F plus, you will have at least one round where there will not be any failure, no failure. And in during no failure round, everyone will share whatever information available with it. So that's why the total information available with all the sites, that will be same. And that's why the decision will be correct. So that's why F plus 1 rounds are required. Like we can take this example, say there are 5 failures, then it has to be executed for 6 rounds. Like out of this, there is 5th round where there is no failure. Now you may argue that if we can have consensus in the 5th round itself, then why at all we are executing at 6th round? The point is that we do not know in which round there will be no failure, because we are assuming that there is at least one failure in every round. Total there are F failures. One round, so this no failure round could be here, could be here, could be here, or it could be the last round. But at least if you execute the algorithm for F plus 1 rounds, you will have at least one round which is failure free. So that's why eventually we will have the decision. It was a crash failure. Now a Byzantine failure. So a famous problem that was proposed by Leslie Lamport, that's the Byzantine generals problem. This problem is that a few generals, they want to decide about a particular war, that whether there is we should attack or we should retreat. That is their problem. And since there are multiple troops, there are many troops. So each general is not in the vicinity. They have to talk with the messages. They have to communicate with the messages. So that's why this problem is called the Byzantine general problem. So the question is, all the generals should agree upon a particular plan of action, like whether it is to attack or to retreat. Now, there could be some traitors. Traitor means they are not loyal. So our question is, or the problem in hand is, that despite the presence of some traitors, the loyal generals, they should not be blocked from reaching agreement. That is the problem. This problem can be translated in this form, in a digital form, you can say. Like say this one is a traitor. So traitor may send, like say if you consider for attack it is 1 and for retreat the code is 0. So 3, that it is a traitor. So traitor may send say attack to 1 and it may send retreat to 2. Means it may send the conflicting input to different, or it may not send any input. So despite this, our requirement is we need to take a correct decision, and that should be a consensus decision. So for this purpose, how we move that now the information which is available with every journal or decision of every journal that need to be shared. So how we do it? We do it by a OM. OM is called the oral message algorithm, means the messages can be forged here, oral message. So here at least 2x plus 1 loyal journals, where x is the minimum number of. If there are x traitors means the faulty nodes, then at least 2x plus 1 loyal we need. It means the total number of nodes, total number of journals, that should be 3x plus 1, x disloyal and 2x plus 1 loyal journals. So how we do it that? Like here, say this is the commander, say H is the commander. So it will send its decision, for example, say attack or retreat, so to all other generals. Then afterwards, a general which has received some decision of the commander, that general will share with other generals or other lieutenants that what was the decision of H, means whether H has sent attack or retreat. They will say it means now this site that will have an indirect, one is the direct with H and other one is from J what H had said. Now similarly it will also share with the J. So in this way, about one report, direct report, we have four more indirect reports. So in this way, in order to guarantee that we collect first hand report like here, then second hand report, then third hand report, so on and so forth. In this way, by transferring this information that what H has said, then you get from J what H has said, then you get from K what H has said. So that's how the total, by this process, from third hand information, we are trying to decide correct second hand information. And from the second hand information, we are trying to decide the original message. So in this way, the number of messages are very large. So here we have seen two examples. One is for cache failures where total number of rounds required F+1, and for Byzantine failures also F+1 round execution. But total number of processors, total number of nodes, in crash failure it could be F+1. However, in Byzantine it should be 3F+1, and of course it is the polynomial algorithm, which they have polynomial time execution. Now question is why 3F+1? Like previously we have seen why F+1 rounds of execution, then why 3F+1? Because F is the total number of faulty nodes or faulty processors. So failure could be of two types. Number one, that if a faulty process is not sending any message, or it may be sending incorrect message like a Byzantine message. So not sending, it did not respond and responded. So for example, you have total n nodes and there are F are faulty. Now question is, for example, the F nodes which did not respond, did not send, they were simply crashed. They did not respond, but they might be the correct processes. Since we are allowing F failures, so who did not send any information, that was a non-faulty process, correct process. So now you are left with n minus m process because there is no input from F. So out of n minus F, now from where you have received the response, they can be faulty because F is the faulty processes. So n minus F minus F. So these should be greater than F because we need to take a majority decision. So n minus F minus F, that can be solved as n is greater than 3F+1. So that's why 3F+1 processes are required and F+1 rounds. One simple example of agreement which we every day we see, that is the distributed commit, the transaction. So in a common distributed commit which we have studied in our undergraduate classes, that in this on every site there is a transaction manager, and it is the responsibility of transaction manager to decide whether abort or commit, and all transaction managers should agree on abort or commit. So here we can represent the entire network as a completely connected network, fully connected network, and or a graph, and in that graph this decision is being taken. So all sites, they are distributed, several distributed sites, and there we take a commit or abort. So this is another example of consensus algorithm. The correctness is, of course, agreement. No two processes decide differently whether to commit or abort, so everyone should be commit. There is one very interesting twist here, that in the validity here, if any process starts with 0, 0 is the only decision, because, and if all start with 1, no faulty, 1 is the only decision. If everyone say commit, then only commit, and if even a single said abort, then it has to be aborted. Like for example, you initiate a transaction on Flipkart, say to purchase an item, for example, to purchase a t-shirt. So this transaction has to be endorsed or has to be decided by three parties. One is you, who has initiated. Second one is that your bank, which has the which will check whether you have the sufficient balance, and third one is the site which is providing the supply, the t-shirt or something. So once you if everyone agrees, for example, the t-shirt is costing, say for example, 1,000 rupees. So initially it will check that whether you have sufficient balance in your whether you have sufficient balance in your account. If it is more than at least 1,000 rupees, then bank will say yes. Similarly, if the t-shirt of particular type which you want, say particular, say 42, so or particular color brand, it is available, then Flipkart will say yes, and afterwards you allow, okay, go ahead, means the money can be deducted. And so If anyone says no, for example, the particular brand of t-shirt is not available, then of course this transaction will not. So that's the difference between a general consensus and a distributed commit. So this is a kind of asymmetry. So for abort, anyone can abort, but for commit, everyone should commit. So that is the distributed commit. Termination, here we see that because transaction managers are used, so if there is no failure, it is all right. But you may assume a scenario where a failure has occurred, then this here it will be blocked, because at one side you have sent some message and afterwards there was no decision, so that will be blocked. So that's why a two-phase commit is not successful. So that's why we use a three-phase commit, which provides this talk. So another very famous algorithm for consensus is Paxos. It's a very famous algorithm that was by Leslie Lamport. Here, this is working in a reliable environment, and means the asynchronous environment, unreliable machines, multiple machines posting different. So this algorithm is a quorum-based algorithm. Quorum means like we have a quorum on a particular, it's like say in a parliament or in a house, the decision will be in favor of the majority. For example, so there are 100 people, 100 members of that house. Then what 51 decide, the rest 49 need to follow that. So that's how a majority. So if there are F faulty processes, then 2F plus 1 node in the system. After that is requirement, and they guarantee progress. This is the setting of this Paxos algorithm. The question is how it works. In Paxos, different nodes are assigned a different terminology, a kind of a role of nodes. Like client, you understand, who issues a request. A proposer, which proposes some value like in a binary consensus, it was 0, 1 or any other value. Acceptor is a node which can decide that whether a particular value must be chosen or not chosen. Learner is a node which does take decision, but decision will be conveyed to that node. And leader is a special node. Why leader is required, that we'll see later on. But for the timing and role of these nodes, it's not a fixed. The role may change. So it means how a value will be chosen. So if there is, the question is, if there is a single acceptor means who decides whether value will be chosen. If there is a single acceptor, then it is very simple, straightforward, and of course, but it will not be fault tolerant, because a single node that may fail anytime. But you have a number of acceptors, then there has to be consensus. So a value is chosen if the majority of acceptors have accepted it, and majority of accepted it. So, and accepted does not mean it is chosen, because accepted, it is not final. Once it is accepted, then another round that will be required for choosing that value. So it is like this. The setting is like this. So proposers could be more than one. They can propose some value, and acceptors, they will decide and they will inform the learner. That's how the protocol works. It is this. If proposer proposes some value that it sends to the acceptor, you just follow the red arrow. Acceptors will promise that we will not accept any proposal which has number less than n. For example, proposer has proposed n. N is 5, for example. So acceptors will promise that we will not accept any proposal whose value is less than 5. That is a promise. So once this promise is returned to the proposer, then proposer will again send another request that accept. Now you accept my proposal. So previous was a promise, and now it is you accept it. So promise that I will not do. Promise that I will complete this lecture in 1 hour. And then after one, accept. Now, here also, if majority accepts it, then this will be conveyed to the proposer, and afterwards it will be a decide. So decide could be a kind of commit, or otherwise it is abort. So here, the critical thing is that a promise that I will not accept a proposal whose value is less than n. That's very important. Like, so this is called from proposer a prepare phase, where it will send a message with some value, and by acknowledgement mean that is the promise. Proposer acceptors will say promise that okay, I will not accept any value less than n. Then afterwards, proposer will send, now you accept my proposal. Then if majority acceptors accept it, then there will be a commit decision, and everyone will be informed that now decision is commit. Otherwise, it will be aborted. So that's how the Paxos works. Now, question where the question of leader comes. Leader is a central node or a kind of coordinator. The problem lies in the FLP host. That previously we have seen that in an asynchronous environment, with fault tolerance means all three we cannot have at the same time: fault tolerance and termination, and as well as the agreement. We cannot have. However, we are getting it. So how to get it? So like we see this execution of these three sites. So this shows the timeline or time axis. So for example, a proposer A has sent a message. My proposal is say 1. Proposal number is 1. So if everyone promised that, okay, no problem. So promise is received. In the meantime, say there is another proposer B, because there could be any proposal. So B my proposal number is 3, my value is 3. So since all the acceptors have promised that we will not accept any proposal whose value is less than 1, then because it is a higher value, so then they will accept it. They will promise for 3. So they have sent promise to A that we will not accept less than 1. Now they will send promise to B that we will not accept less than 3. Naturally, if they will not, they have promised that we will not accept less than 3, then proposal of A cannot be finally decided in favor. So now there will be failure. So after this failure, then what is the choice with A? A will put another value, propose another value which is more than 3. For example, it proposes value 4. Then now whatever the proposal of 3, that will be gone, because they have promised that we will not accept more than 4. Earlier they have promised 3. So in this way, only two sides, only two proposers, they will be continuously racing. That proposal number 1 promised, not accepted. Then proposal number 3 promised, not accepted. 4 promised, not accepted. So on and so forth. So that will be a race condition. Comes the role of a leader. That now it is for leader to decide that once you have the leader, then leader will decide, look, out of these so many proposers, this will be called the actual proposer, or this one I decide that he will be the proposer, and then whatever is its proposal, that everybody need to accept. So that's how the leader. So here means the due to leader, now liveness is guaranteed or termination is guaranteed. However, safety was guaranteed earlier, fault tolerance is there, but liveness is guaranteed due to leader. It means still the FLP theorem is not violated. Means still FLP exists, that we cannot have all three together or the simultaneous. And applications of Paxos, there are large applications. Leader election is one. Of course, it is also a consensus problem. Fault tolerant replicated machines where all replicas in the same state and same input sequence. Distributed transaction, I have just given you the example of transaction. Distributed file server, like some information, like we access some information from the Google or some banking information, and that information is distributed across multiple servers, but we have the consistent view of that information. So that is due to agreement. So these are few uses of Paxos. Paxos is, of course, for the dashboard. Now here comes the big one, the Byzantine fault tolerance. It is called the PBFT in short. PBFT, practical Byzantine fault tolerance. So here system model is little different. Here there is one client. So of course they have taken some idea of Paxos, but of course it's a different proposal. How it works? That there is one client and there are multiple replicas, as if the information, like we can say the banking information or some geographic information, that is stored on multiple servers. Like if you consider the information, the banking information, so RBI information, that is available on multiple servers. Like if they put it at only one place and say there is some mishappening, fire or some terrorist activity or anything, hacking, then all information will be gone. So that's why they put this information on multiple machines, and those are called the replica. They will have the consistent copy of the same. So at one site, if there is some mishappening, some fire, terrorist activity, hacking, anything has happened, despite that, the banking information is available. So that's the purpose of replica. So client and replica. So here what happens, that client means replicas, they will inform this client sends a request, like the red arrow, you can follow it. That client sends a request to a replica, and the replica, a consensus will be carried out, that everyone will decide, yes, this is the information, or this is the consistent view of the information, and that will be conveyed to the client. So that is the purpose. Here the failure is now Byzantine. Mind it, it is arbitrary, not crash. Let us see how this algorithm works. So first we will do the system model. So what is that? Number one, that it is an asynchronous distributed system. Asynchronous means there is no bound on the message delivery time. However, it is finite. One thing is important. Secondly, the PBFT uses cryptographic techniques to avoid spoofing or replays or loss of message, corrupted message. So all these are controlled by cryptographic technique, means public key signature, message authentication codes. Digest, you understand, because a message is represented in the form of a numeric or sequence of digits, and that is unique for every message. Means as a kind of a text, the text is translated or decision is translated in the form of a numeric message, and that is uniquely added for every message. So that is a digest. This is created through a collision resistant hash function. Collision resistant means, number one, the hash function is irreversible. Once from the message you have created a hash value, then from the hash value you cannot generate the message back, number one. And number two, for each message it generates a unique hash. So that's why it is called the collision resistant hash function. So the important thing, only 2 points you remember. Number one, that it is a asynchronous system. It can delay, duplicate, or deliver messages out of order. And number two, that messages are the spoofing, replay, failure, etc. That is controlled by these cryptographic solutions. We will not go in detail. We might be in some other lecture you will be discussing that. Okay. Now the adversary model. How the traitor or how the adversary will behave, the faulty node, how it can behave, what it can do, what damage it can do. Can coordinate faulty replicas. It can capture 2-3 replicas and try to manipulate them. Number two, it can delay correct nodes, but not indefinitely. Delay means excessively slow, like some network or line has become excessively slow. But of course, it is bounded. Cannot subvert, as we have already seen that cryptographic methods they have been used. So it is assumed. So that we see that in PBFT, again, the FLP is honored. That still exists. Means you cannot have all three together. That means agreement and termination as well as the failure. So or cap also for that case. Means consistency, availability, and the partial. So all three you can add. That's why we are using cryptographic technique to avoid FLP. Now the kind of service it provides, safety, that you understand that something wrong should never happen. Fault tolerance is of course that utmost required that we want to do. So it tolerates F faulty, and total 3 F plus 1 nodes are required, that we have already seen that why 3 F plus 1 should be there. Now it minus F, because F is the faulty, so 2 F plus 1 is left. Out of 3 F plus 1, F is the faulty, so 2 F plus 1 are left. So 2 F plus 1, still it is a majority. So that's why if all 2 F plus 1 are good, no problem. But if out of them, if F are faulty, then again we have the F plus 1, a majority. So that is to ensure safety. And third one is the liveness. So you may argue that if you are ensuring safety, fault tolerance, as well as liveness, then where is the FLP? Of course, it is still. Yeah, anybody has some question? Hello. So liveness, for liveness, it assumes partial synchrony. PFT assumed a timeout mechanism, and to ensure the liveness. So here also, that since we assume a timeout, so that's why. Otherwise, you would have argued that FLP impossibility has. So a strategy is that primary runs the protocol, and round by round it is execution. And here replicas keep vigil on the primary, because primary can also be faulty. That's why leader can also be faulty, like we have seen in the BGP, Byzantine General's case, that the commander can also be the traitor. So if primary is faulty, then the primary will be changed, and that is called view change. View means a particular configuration of primary replicas, which under execution of a particular primary, that is called a view of execution. And if primary is found faulty, then we will change the view. That's why we call it the view change. View change means the changing the primary, changing the leader. So key difference is replica might be faulty. So that's why the inventors of this protocol, means Castro and Lisco, they introduce a pre-prepare phase. In Paxos, we have seen a prepare and then commit. Here, pre-prepare. Now, question is how it pre-prepare works. That client sends request to primary in normal case. Then primary sends pre-prepare message to all. So this pre-prepare is because straight if we send the prepare, it means we have not checked the cryptographic techniques which have been applied, that message can be spoofed, corrupted, or modified. So through cryptographic, it has been protected. So during pre-prepare phase, actually we check the correctness of the message. If it is correct, then only it go beyond that. So that's instead of straight away prepare, it will first go to a pre-prepare phase. So pre-prepare phase, replica checks the pre-prepare, means if it is correct, then send pre-prepare message to all. Pre-prepare message to all. And then replicas wait for 2f+1 matching prepares. If 2f+1 matching prepares, then it will send commit to all. Then if 2f+1 matching commits, then it will execute and send result. Afterwards, if the client accepts results, if f+1 identical replicas are required. So identical reply are there. So this is the sequence how the BFT works. So it's basically a three-phase protocol, and pre-prepare plus prepare, they guarantee the ordering of the request, the total order. Total order means order will be in the, because every request is assigned a unique sequence number, just like a student is assigned unique roll number in the class. So from that roll number can be accessed, like sometimes we are assigned a unique number for our account or something. So this unique sequence number, that is assigned to every request. So pre-prepare plus prepare, that is unique assigned sequence number, and that is ordering. And afterwards, once this is ordered, then this is a consistent across all the views. Means even if the primary is found faulty and primary is changed, even then this will be a consistent order. So you understand the view. View means corresponding to a particular primary. So everyone, R is the total number of replica, it is 3f+1. So V mod R, so it is 3f+1 means it is 0 to 3f. Means primary, any node can be primary up to 0 to 3f. So the sequence will be request, pre-prepare, prepare, commit, and reply. So if we see an execution like this, that initially client will send request to all replicas and primary. Once this request is received, then a pre-prepare message, means primary will send pre-prepare to all the replicas, and replica will wait for 2f+1 prepare messages. Once it is, you can see this 2f+1, everyone gets 3. Then it will send commit, and commit is again 2f+1 commits. So each one will wait for 2f+1 commit. Once it is received, then it will send the result, and the client will accept the result if it receives 2f+1 replies. So that's how the BFT works. So in this, we have seen the consensus in for crash failure. We have seen the flood set algorithm. Then we have seen for Byzantine General's problem, which was in asynchronous setting, in asynchronous environment, introducing some synchrony and handling that problem. So that was for the Byzantine failure. Then we have seen the Paxos, that was for crash failure, and then again the Byzantine failure. So these are the different algorithm, classic algorithm they have been used in the for having the consensus. So consensus is that makes the core of your blockchain. So the question is how all this relate to the blockchain. So as you are aware, because already you have gone through many lectures and previously also you might have some background. So blockchains are decentralized ledgers, are distributed ledgers. And we know that it is not controlled by a central authority. So since it is not controlled by central authority and it is a ledger, so of course all the bad actors, they can get the economic incentives by playing with these ledgers, or by introducing something wrong in these ledgers. So, and they can be arbitrary because machines are not in our control, they are distributed across the globe. So Byzantine fault tolerance, which is of course the arbitrary fault tolerance, so that is much needed for the block. So it is not only the BGP or Paxos or PBFT that is able to handle all the problems, because every algorithm which is developed to or designed or proposed to handle a particular problem or to handle any challenge, that has its own pros and cons. So always there is a requirement of research for taking it forward so that it can handle the other problems. So, many algorithms have been developed beyond this PBFT also, and some of them you might be aware of it. So Byzantine fault tolerance is much needed for blockchains, and in the absence of this BFT or Byzantine fault tolerance, what can happen? A peer is able to transmit and post false transactions, and if it is so, then of course the reliability of the blockchain that will be compromised. So that's why BFT is to be Byzantine fault tolerance need to be guaranteed. And the biggest problem is, since there is no central authority, like previously we have seen, in order to ensure liveness, or in order to ensure the correct execution in most of the protocols in Byzantine fault tolerance, like we have seen PBFT or BGP, we have seen that there is some leader which takes care of this. Since there is no leader, no central authority in the blockchain, so nobody is to take care of this. Who will repair this? Who will handle this problem? So that's why a consensus that makes the core, and BFT is the utmost requirement for this. There is a question. Okay, now you can. No, I am done. So you can just switch on your mic and raise the question, and I will be happy to answer them.
Thank you very much, sir, for this insightful expert talk. So all of us were learning or using this consensus mechanism word, and we were using BFT or PBFT somehow. And also we will be using these protocols for Ethereum implementation as well. So now we have a good insight how these algorithms at the backend actually work, and why fault tolerance is an important concern when it comes to validation of blocks on a blockchain. So PBFT, very specifically, out of many consensus protocols which have been defined in literature for blockchain, so PBFT has come up as one of the promising consensus protocol, which is frequently used by the permissioned blockchains. We have Hyperledger, we have Stellar, we have Ripple. These are blockchain platforms which are using PBFT consensus because it requires less effort, first of all, and majorly the benefit is that it comes at the cost of anonymity on the system. So this PBFT consensus is a promising consensus which is used by many platforms on permissioned blockchains, and this is where all of us were able to know how PBFT actually works and what are the intricacies. And we should all know that consensus is not just running by the name of the algorithm. Behind this algorithm, we have to ensure properties, like we have to know what is agreement validity, because without these properties or characteristics being fulfilled for any system we are applying to, say it's a blockchain we are applying this system, so without being like commitment to these properties, we will not be able to run it successfully for any application. So this way consensus has come as a wonderful session from your side. So we are very, very thankful. Sir is a core researcher in distributed systems. So I collaborated with sir in 2008 as my PhD supervisor too. So I wanted to announce in the beginning, but I will take this opportunity again to tell the participants. So I did PhD under sir from 2008 to 2011. So we did on distributed transactions where we handled proactive detection of faulty nodes in transaction processing. So this was the work we had collaborated upon. Thank you so much, sir. Now we are open to queries. So we'll be happy to learn know some queries from your side, or you can type as well.
You can just switch on your mic. It is better.
Yes, sir.
So I'm getting some thanks, but that is not enough. But I'm expecting some questions. At least few questions. If the number of node are more in the network, just could you switch on your mic and tell, because I'm not able to clearly read it. Is
Prashant sir, could you ask your question? What you want to ask?
Okay, sir. Which situation we are to apply for the Byzantine fault tolerance and Paxos algorithm, sir?
Actually, Paxos is not for Byzantine fault tolerance. Paxos is for crash failure, and Byzantine is arbitrary. Means PBFT, as Dr. Saini has told, that PBFT is for Byzantine fault tolerance, and BGP, Byzantine general solution, that is for the Byzantine failure, arbitrary failure. But Paxos and flood set, they are for the crash failures. Crash means once machine has stopped working, then it will not respond. That's how the. Any other question? Am I clear? Any other question? No, hopefully it is done. So if there's no questions, then I must thank to all of you, and especially Dr. Saini, for giving me opportunity to speak in the lockdown. So, my focus was not to have a kind of very dark lecture, because I wanted to discuss the core content. Sometimes we have many very ornamental lectures during such type of the gatherings, but I always stick to the fundamental concepts, because sometimes that becomes very, very important. Or sometimes new researchers, especially the young researchers or PhD scholars or young faculty who start working on a particular area, so they straight away start reading the research paper and trying to find something from that. So it is always better to first study or understand the fundamentals, and then afterwards the life in research becomes easy. So, Dr. Poonam, should I thank you?
It is used in the cryptocurrency or Bitcoin.
Yeah, hello.
Yeah. What are the other applications precisely that can be?
So the question is, I have given one slide. If you could have seen, because if you say other application, means wheresoever, not necessarily I'm not pinpointing the application. Wheresoever multiple parties need to agree on a particular decision, there the consensus is applicable. So, for example, I say that there is some geographic information. It is distributed across geographic information or banking information. It is distributed across multiple servers, and you want to get that information. Now, then, for example, you want to get, I also want to get. Then about with that information, we both must get a consistent view of that information. Since that information is on multiple servers, so I may access from server A, someone else may access from server B, and the question is whether we both are getting the consistent view, same view of that information. So for this, the consensus is required. So that's why the wheresoever agreement comes in picture, like even a small case, that in a small case, for example, say in a lab there are 50 students and there is only one printer, and you want to decide that who will be next to get the printer. This is also a consensus problem. So it has to be handled in the similar manner. Means everyone, if I decide that row number 15 will be next to access the printer, then everyone should agree on this. This is also an agreement problem. So wheresoever the multiple parties need to agree on a particular decision or value, that is related to the consensus, and we all must know it.
Thank you.
Hope I am